So it's my pleasure to tell you a little bit about our work in Parkinson's disease. I'm going to start with the Alzheimer's story because I think it sets the context and in connection with what I'm going to tell you about in relation to Parkinson's disease. So I'll do a little refresher on the Alzheimer's story first. I have certain disclosures. We've got funding from Nestle Health Science. I've also consulted for Abbott, Cargill, and Saracen, and we have various funding partners. And I also insist on this being a research description. This is not medical or nutritional advice. So the context is brain energetics in Alzheimer's disease and the dual tracer PET that we've been doing for the past 20 years here. And then a brief look at what we've done with the dual tracers in Parkinson's disease and the implication, I think, to look at a little further at glucose dysregulation. If you're not familiar with it, this is the review that we published 4 years ago now. It's my by far my most highly cited and most impactful paper with its proceedings of a meeting that was held in Paris with the participants that are the co-authors on it. And I learned at the end of the meeting that I was the one who was being delegated to write a review that was reported on the whole thing. So it was quite an exercise in playing catch up with some of their talks. This is the classical sort of image that I would use to show you the problem with brain glucose metabolism. You've seen various images already in Alzheimer's disease. Wow, this is hard to manipulate. But the parietal cortex is the area that has the problem with glucose metabolism. It should be, the brain should be consuming 100 to 125 grams of glucose per day. And in mild cognitive impairment, that deficit is on the order of 10 to 12 grams a day, and it gets worse as the Alzheimer's disease progresses. So that's the nature of the problem. It's been well known for a long time. And there's been so much interest in the amyloid story, the presence of amyloid, the defining feature, if you will. But the fact of the matter remains that the uptake of FDG or glucose by the brain is better correlated with the cognitive performance of the individual than is amyloid. So correcting amyloid does not necessarily improve cognition. And that's one of the reasons why we've continued to work so much on this. And the concept, as you know, of the hybrid car, we call it the alternative fuel. But there is this shuttle between ketones and glucose that is so important for a healthy brain. The other thing that I think is not well understood is that glucose uptake by the brain is largely driven by the brain's activity, the brain cells that are active. And so you can have just eaten a large amount of glucose or sucrose for that matter, and it doesn't push glucose into the brain, which is what happens with ketones. If they're present in the blood, as Frédéric mentioned earlier, in reference to our work and others, the plasma concentration drives the uptake. And teleologically, it makes sense because when this is starting to go down, it's usually a signal that insulin is going down, and that's normally the brake on ketone production. And so the timing of the replacement of glucose by ketones is obviously fundamental to keeping the brain working. This is the protocol that we use starting over the past 20-some years now, quite a few scans and publications. The ketone PET first, a washout period, the FDG PET afterwards. Sometimes we do the MR in between it when we're able to fit it in, or within a couple of days at the most. So we have the anatomical situation. We also have the resting state fMRI and diffusion. And critically, if you want to know, and Corinne, I'm so glad to see you present quantitative results for the glucose. You can't quantify the glucose or the ketone uptake without the blood samples. And so a lot of work shows a statistical difference, but not a quantitative difference. I think Frédéric showed this image, and I just draw your attention that with the ketones, as you go from the control individuals to the MCI, to the Alzheimer, you don't see a decrease as you do with the glucose. As you go towards Alzheimer's, you get this green that starts to emerge. And in some cases, you actually get an increase, which I'll show you quantitatively. So this is really the basis of this question that these samples, these images are taken within 90 minutes. We've reported them on several occasions by PET. I think it's Frederick's results with the transporter expression. It confirms these results. But there are some quite old results that have shown this by arterial venous difference across the head. So there are different techniques that show that this is a fairly robust observation. And what I want to do is use the same approach to show you in a couple of minutes what we see with Alzheimer's. So if you look at those qualitative images, what this means in terms of the capacity to transport the K constant value in mild cognitive impairment, you actually get an increase in the capacity to transport ketones, which is different, opposite to what you see with the glucose. So this is confirming basically quantitatively the difference that we see. And this increase may have some connection with the hyperactivity seen in functional connectivity in the brain in mild cognitive impairment that precedes a decline in functional connectivity as Alzheimer's disease progresses. So it's really based on this that if you're having trouble getting glucose into the brain, why not try to exploit the alternative fuel a little further? And as Frederick showed from our earlier work, not only do the basal levels of uptake, fasting value or postprandial value around 0.1 millimolar is going to give you somewhere in this cluster. But as you push the ketones up above 1 millimolar, the linearity is on the same slope as it is for the healthy controls that have gone through these extended fasting studies that were done back in the 1960s and 70s. So there's every reason to believe that the Alzheimer brain can utilize the ketones when they're supplied. And the question becomes, how do you raise these ketones sustainably and safely? And this is a question that some of you have been attaching with various approaches. And the implication is that it's one thing to get the energy in, but as you know from earlier presentations, we see this relationship between cognitive performance and ketone uptake by the brain. It's not a very strong relationship. This is the first time we've ever tried to utilize a medium chain triglyceride. We didn't know what the maximum tolerated dose would be. We didn't know exactly what the effect on the blood glucose was going to be. We were funded and we had to figure out literally overnight how we were going to make a drink that people would take for 6 months. So you see an overlap. This is a delta value. So it's at the start of the study, before to after. So the delta is greater for the MCT, but there's a lot of overlap with the placebo as well. And it's just impressive that we were still able to see a positive relationship. It's now approved as a healthy product in Canada for the last 2 years, and it led to the Cunnane study. So this is one approach, amongst others, to increase ketone access to the brain and to try and slow down cognitive issues that develop with aging. We expected to see that with exercise, we would see an improvement because of improving, we thought, insulin sensitivity. We expected to see an improvement in the uptake of glucose by the brain, but we didn't. In fact, we saw quite an impressive increase in ketone uptake by the brain. And that the time it took to complete some of these executive function tasks decreased. So these are negative values. So a negative slope is an improvement. And it's directly associated, well, inversely associated with the change in plasma ketones. So this is what is bringing me to the Parkinson study, where we know that exercise can be beneficial as well. And I thought if we can improve ketone transport into the brain, with exercise, and we can provide more of a ketone supplement, maybe we can get a synergistic effect between them. So that partially answers the question in the title, why combine them? The fact is, it's another form of neuropathy in the brain with alpha-synuclein, which forms aggregates of Parkinson's disease, the motor and the non-motor problems, and deteriorating production of dopamine. The substantia nigra seems to be a central part of the brain that is affected. Very little really known about brain glucose metabolism in Parkinson's disease. A couple of studies, but some empirical studies with interventions with shadow boxing, with dance, with running, and seeing some improvement in the symptoms. So again, led us to think, along with our results with exercise increased keto uptake in Alzheimer's disease, that maybe we could combine these two to potentially be of benefit. There are some small studies on ketogenic diet in Parkinson's disease, nothing that you would consider to be convincing. So as Amir showed, slightly redrawn, but it's the same information. We have some baseline information, cognitive tests, the MRI, the PET scans done, and then the supplement period in the Parkinson. This is the Parkinson patients only in the study. 2-month intervention with the exercise and the supplement. The supplement contained B-beta hydroxybutyrate, 24 grams per day, plus 1 gram per day of nicotinamide riboside, and then you repeat the tests after 2 months. The demographics are that we recruited 10 people, a 50-50 split with the men and women, 72 years old. You look at this profile and you say, you know, these are essentially healthy older people, apart from the fact that they've got this diagnosis. A BMI of 26 is usually reasonable at 70 years old. An MMSE at 27, 28 is pretty good. Physical activity scores. Ketone values, however, it's a red flag for us. These are probably the lowest ketone values we've seen in anybody, anywhere so far. And I'm going to come back to this glucose, which looks pretty reasonable as well. So metabolically, there doesn't seem to be anything outstanding about these patients. When we look at their plasma ketones on this treatment, so the baseline is before any treatment. This is after one single dose of the ketone supplement with the nicotinamide riboside to see its effect by itself. Then the 2-month intervention combines supplement every day plus 3 times a week of the exercise. So you get a big increase in the ketone response in relation to baseline, and you get a further 50% increase if you're doing the exercise. So we're seeing a synergistic effect on the plasma ketone response in the Parkinson patients. Great. And if we look at the brain uptake, these are values that were published by our colleagues at Nestle when they were first looking at these ketone salts. So when you look at take the dose at time 0, it'll be back to baseline around 3 hours later. So what we try to do is schedule the PET scanner roughly an estimated peak. It's never the same in everybody. So these values are taken at approximately the peak time when you're looking for plasma ketones. So CMRK is the cerebral metabolic rate of ketones. So it's a global value for the brain, the whole brain. Very low before they get the supplement. The single dose will give you a value of nearly 2, and the combination gives you a value of nearly 3. So again, there's not more ketones being consumed, but exercise is helping mobilize some ketones endogenous from probably, and more is getting into the brain. So as a contribution to brain fuel metabolism, they're down here at well below what you'd expect in a healthy adult, which would be between 3 and 5%. The single dose at that peak time, ketones would be contributing 9 to 10%, and with the exercise, about 50% more. So we can have an impact, and this peak, of course, will happen if you take it twice a day. The peak will happen twice a day. If you're on a ketogenic diet, then that peak will be extended over a longer period. So different strategies for different situations. But this is a sort of an impact that you can get on brain energetics and Parkinson's disease. This is a small study with 10 people. The purpose was to look at the metabolic situation. So we don't have any, we have some memory results, which I'm not going to go into, but the clinical condition of the patients was not really assessed, and it wasn't the purpose. So I have nothing to report on whether they're actually better or not. What I want to do is bring up another aspect to this, which I think is needs to be looked at a little more in depth, and that is the question of glucose dysregulation. So one thing that seems to be important both in Parkinson's disease and Alzheimer's and probably other forms of neuropathological disorders is that insulin resistance gets installed in the brain in some way. There's some evidence that some of the drugs that are being used for type 2 diabetes can be beneficial in Parkinson's disease. And there's unfortunately some evidence that the drugs being used in Parkinson's disease can, in fact, obviously unintentionally, be unfavorable to insulin signaling, at least in muscle. It's a 20-year-old study, but I have no reason to think that it's out of date for any particular reason. So the question is, could these drugs, in fact, you're trying to treat the disease and the acute symptoms, you're trying to keep that person functional as much as possible. Maybe you're contributing to the long-term ineffectiveness of the drugs, and perhaps it's similar. It makes me think a little bit of the situation with antipsychotics in psychiatry. Are we making the situation gradually worse? And if there is a problem with insulin signaling and perhaps type 2 diabetes, which is what has been proposed, what is striking, as I showed you in the earlier demographics slide, is that our plasma glucose values are 5.5. Who's worried about that if you go and see your family doctor? It's totally normal. So, assuming that value is technically correct, and yet there's some problem with insulin resistance, then this isn't a very good measure of glucose intolerance. So how should we be measuring it to get a better understanding of the impact of metabolic regulation on this type of neurometabolic disorder? And a similar sort of question is that if the ketogenic diet is beneficial, as it's been reported, what's the impact of ketones on brain glucose transport? So if we come back to what I showed you earlier, I showed you the first bars in the middle and on the left in both cases before, and I showed you that in the ketone uptake by the brain is increased in mild cognitive impairment and then comes back down in Alzheimer's disease, but it's still as high as in the healthy controls, whereas it's going down for glucose. So the bar is at where the healthy older controls are, and you can see that the ketone uptake in Parkinson's disease is totally normal, at least the capacity. And when they are on exercise plus the ketogenic supplement, it doesn't change the capacity to uptake ketones. So the total uptake is dependent on the plasma value, which does go up. So total uptake goes up, but the actual transport capacity has not changed. Whereas with glucose, it's going down. And ketones, glucose up, the capacity to transport glucose in Parkinson's disease is definitely at least as bad as in Alzheimer's disease, and perhaps worse. We have a smaller sample size. And maybe with this intervention where they've taken the ketones and exercise for 2 months, we may be seeing an effect. It's too small to see statistically, but it's encouraging to think that we can make an improvement, because if that were to become statistically significant and the bars were smaller, that improvement is really important in the total fuel supply to the brain. So what's going on in the substantia nigra, where the dopamine is supposed to be produced? The only comparison we have right now is between our Parkinson's before and after versus MCI. It's what we call the Break AD study, but it's MCI patients. And all I can tell you at the moment is that if you have MCI, you have better glucose uptake in your substantia nigra than if you have Parkinson's. That may not be a surprise, but what's encouraging is that there may be in some individuals, we can still turn that around. And perhaps by increasing glucose uptake in the substantia nigra, we can in fact produce more dopamine. I mean, maybe, we don't know. What we see overall in the whole brain is that there's very little difference in glucose uptake before and after this ketone plus exercise intervention. So again, when you get the overview of these major brain regions, it could mask what's going on, or maybe that's going to never turn out to be statistically different. So these are preliminary data, and tomorrow morning, both Frederic and Corinne are going to come around to the imaging center. And we're going to show them the new scanner that's being built that has a higher resolution, a higher capacity to go on and collect these data more accurately than we can with the regular PET scanner. So we might be able to find something that is going to help us relate the energetic states of the substantia nigra per se. So this is specific to the substantia nigra. These are global values for glucose uptake across the brain. I'm encouraged to think that we could do something because the substantia nigra is in the white matter area. And this is a study from our mild cognitive impairment study, and the dorsal attention network is a white matter tract in which we see that MCT can increase glucose uptake in the white matter. So it's possible that we're going to have a beneficial effect of the ketones within the brain in liberating some glucose or making it more available. There's a lot to explore that would help us understand what's going on there. So ultimately, when we come back to this image that I just showed you, what I'm really interested to know about is how do we get this to move further? Do we have to force them to do more exercise? Do we have to force them to take ketone ester, drink much as they maybe test that? Or how do we maximize this effect in order to improve the ketogenic potential? So one thing that we're thinking about is doing it by improving overall glucose metabolism. You can use GLP-1 inhibitors, receptor antagonists. We can use intermittent fasting. We can use exercise. And we can reduce carbohydrate intake. Maybe we should do that. Now, Alexi talked about this earlier, and I wanted to bring up a paper that I think is extremely important in this context. It's David Unwin's work in the UK, where they follow people with a reduction in carbohydrate intake. It's an 8-year study. It's been going on. There's nearly 200 people that have completed the trial, and they can show, you were talking about diabetes remission. That's the target. Get yourself under 77 grams of carbs per day or 15% of energy, and you can achieve remission. So we don't need to go to 20 grams a day like in a ketogenic diet. 77 grams a day is manageable for more people. It requires weight loss, as you mentioned, and their observations are saying the hemoglobin A1C coming down, plasma triglycerides are coming down. So when you reduce carbs, you're going to increase fat, but there's no smoking gun in relation to cardiolipid problems in relation to triglycerides or LDL cholesterol. So that's what I would call improved glucose regulation. And it's in the same age, no, sorry, this is a younger population, about 62. So how do you do this in an older population? Because Parkinson's disease usually hits at 60 plus. Well, going to a retirement home, and you do a 2-month study with people that are sitting at the back. Camille is back there, she worked with us on this. Isabel, whose friend David provided the lunch. Isabel's a dietitian. She helped him set up the menus for this. And what we looked at in this retirement home is the continuous glucose monitoring, showing just a snapshot of the results, but the critical point is that you can separate the participants. There were 11 with the high glucose started with, and 8 with hyper, I think, sorry, the normal. So the normal blood values, I'm not going to show you the change with the lower glucose intake, with lower carbohydrate intake, because there's essentially no change. The black line doesn't change. That's where you want to be. But those are the hyperglycemics, so they're the gray ones, and they come down after 2 months. In fact, they come down sooner than that, both postprandially and the fasting values. And this is a 30% reduction in carbs. So they're still eating about 130 grams of carb per day. They're not going to go into remission for type 2 diabetes, but they don't have type 2. Some of them are glucose intolerant. It's a 2-month study. We could potentially take it further. But the point is, this is the population that we would want to be studying, and we can get an improvement almost instantaneously with a 30% reduction in carbs. Why not combine that with a ketone supplement and exercise, instead of trying to do any one of those individually and hoping you can put all your effort into one approach and asking too much of the patients for any one of them. So that's what we're interested in trying to do. It was quite well accepted by the participants. Excellent cardiometabolic safety. It's Cannane's paper that's going to be out very shortly. And the surprise was that it was actually mildly ketogenic as well. So in summary, we've got some preliminary data. There is a metabolic mess in the Parkinson brain. That seems pretty clear. It looks like it's worse than it is in Alzheimer's disease. We don't know the nature of the problem. Is this in group glycolysis? Is it in the TCA cycle? FDG isn't able to tell you that. But the good news is that there doesn't seem to be a problem in the capacity of the brain to use ketones. We can improve that capacity with exercise and ketone salt. So if improving energetics is beneficial clinically in Parkinson's disease, it's probably because ketones are involved in correcting the brain energy gap. We need clinical endpoints, so we need to do a new study, and I would suggest we need to do a study that has 3 components: the ketone supplement, exercise, and reduced carb intake. And with that, I thank you for your participation. I thank Valerie and Melanie and Frankston, Camille, and the other members of the team. Chris Alexander Castellano was the one who inspired this project on exercise plus a ketone supplement. He left us to go for personal reasons to go to Quebec City. He's working at the one of the research centers. I think it's the lung and heart one.
IUCPQ.
Yeah, he's part of the administration there now. So, well, the administrating. Whatever, yeah. I'm not sure. I don't want to glorify his name. And the funding partners, and of course the participants. And if you're interested in following what we've been doing, it's on our website. So thank you very much for being here today. I'll be happy to try to answer any questions that you have. Thank you.